Oh, hi there. Welcome to this marvelous Math Monday. What a pleasure it is that I get to interact with the youth of 2023 and show you how to use your youth to transform money into lots more money. I'm going to look at some very powerful math today. So without further ado, let's get going. We're going to be looking at two different concepts today, simple interest and compound interest. And most of our time is going to be spent on compound interest. In our society, compound interest is far more pervasive than simple interest. Simple interest is generally used as informal loan arrangements between people that aren't businesses. It's fine. I'll find it somewhere in my soul to forgive you someday. So, simple interest. This is where you're paid interest, but the amount of interest you're paid never grows. It's based only on the initial amount borrowed or the initial amount loaned. So these create lines, linear functions, because they're always growing by the same amount. So the first differences are constant, so they'll be linear. And the formula to find how much interest has been awarded is simple interest is equal to the principal, which we usually identify as P. Principal, this word means the initial amount invested, multiplied by the interest rate, multiplied by time in years. When we're working with this, it's important to write the interest rate as a decimal. So suppose the interest rate is 5%. As a decimal, that would be 0.05. That's 5/100ths, or 5 cents on the dollar. So that's what that would look like. If you were at, say, 11.5%, then that would be 0.115. That'd be 11.5%. Now, this formula here is useful for how much interest will be given, will be paid. But oftentimes we want a function that shows us how much is the total amount of money available. And for that, you need to add back on the principal to the interest earned. If you invest $1,000 at 10% simple interest, every year you'll be given $100. That amount doesn't change even as your investment grows. And so in the first year, you would have $1,100, in your second year, $1,200, and so on, making a line into the future. So this formula is useful to calculate future value. You'll notice all it is the interest added to the principal, and then I factor out the P just to make it a little bit more beautiful. P multiplied by 1 plus interest rate times time. And that will give you the total amount of money. That's simple interest. In a moment, we'll graph a situation like that. Compound interest, as you can see, the formula looks a little bit more complicated, and you'll notice this is an exponent here. So we're going to have a curve that creates an exponential growth curve into the future, and that's what being young and having a little bit of money, if some of you have some part-time jobs or can do some good earning over the summer, if you can find a way to save some of that and invest it, that curve gets pretty exciting as things start to blow up and take off. So in this formula, the future value of an investment is equal to the initial amount invested, which is the principal here, multiplied by 1 plus the interest rate raised to the power time. And so here is time. And you might be saying, well, what are these C's in here? What are these C's in the formula? We're going to talk about C's in just a moment. When C is 1, when interest is calculated once per year. So supposing you invest that $1,000 at 10% compound interest, after 1 year, you would have $1,100. After 2 years, you would have $1,211 instead of just $1,200 because it's compounding on itself. When C is 1, it basically disappears from the formula. Your rate divided by 1 is just your interest rate, and your amount of time T years multiplied by 1 is just the number of time T years. So in this first situation that I want to look at, I would like you to graph for me Kamala, who has $1 million right now. Must be nice. And she doesn't have another use for it. She doesn't need to buy a home. She doesn't need to buy a car. She can just use that to invest. And she has two options: a 20% simple interest account or a 10% compound interest account, compounded annually, meaning once per year. So C is 1. And when C is 1, this formula will simplify to this. Future value is equal to the principal multiplied by 1 plus the interest rate as a decimal raised to the power time. Yes, that is an exponential function, just like we saw in Unit 4. So these are exponential growth things that you conquered in Unit 4. They're exactly the same. So find for me how much money she would have going either with the simple interest at 20% or the compound interest at 10%. In year 0, we haven't earned any interest, so she has $1 million either way. Find for me in year 5, year 10, year 15, year 20, and year 25, and then graph it on the axes given. Go. All right, let's take a look at the first couple calculations. I'll do simple interest here. And here's my formula. P is multiplied by 1 plus RT. So I'm going to copy out my formula on a blank piece of paper. Principal multiplied by 1 plus the rate times time. And I know that my principal is $1 million. My interest rate is 0.2 because that's equal to 20%. And time is 5 years. So in this case, the future value at 5 years is going to be $1 million. That's substituting in for P, multiplied by 1 plus 0.2 times 5. Well, 0.2 times 5 is 1. 1 plus 1 is 2. That makes sense, because this simple interest earns $200,000 per year. 20% of $1 million is $200,000. So that's how much interest she would be earning per year, and it would never change because it's simple interest. So future value at 5 years with simple interest is $2 million. Because I happen to know 0.2 times 5 is 1, so in there is 1 plus 1 is 2. 2 times $1 million is 2 million. So then I go ahead and plunk that value into my table here, $2 million. Now let's work out compound interest for 5 years. Let's see. Here I would use I'm going to use a different color pen. Here my formula for compound interest looks a little different. Future value of a compound investment is going to be principal multiplied by 1 plus R. When the compounding period is annually, C is 1, so it disappears. 1 plus R raised to the power T. Okay. In this case, P is the same. It's still 1 million. And the interest rate is half. It's 0.1. That's 10% as a decimal. And time, we're looking at the same time. It's 5 years. So in this case, we find the future value to be equal to $1 million multiplied by 1.1. That's 1 plus 0.1 is 1.1 raised to the power of 5. That is hard to do in your head, so do it on a calculator. 1.1 raised to the power of 5 equals 1.6. So in this case, the future value will be equal to 1.6 million. And I might write it down that way, 1.6 million. But there was 1.61051, Mr. Jennings. Yeah, okay, who cares? We're making a graph. Get it close enough. So I think to the nearest 100,000 is enough detail. So that's why I put 1.6 million. Okay, and then I put those in my table. And then I'm going to calculate for 10 years, 15 years, 20 years, 25 years. Keep going. So after much calculation, this is what our values ought to look like on our table. I have the simple interest graphed already. Let's go ahead and graph the compound interest. So we start out at the same spot, so we share that point. At 5 years, we only have $1.6 million. So that's 1.5 right there. So 1.6 is a little bit bigger, so it's about there. Okay, so we're doing a little worse than this simple interest. 10 years, we have 2.6 million. So that's there, 2.5, 2.6. We're still doing worse, and it's actually, curiously, it's by about the same amount. Isn't that interesting that they both grew the same amount between 5 years and 10 years? Because they're parallel there. And then at 15 years, oh, wait, we're even better. We're better than that other account. We're above it right there at 4.2 million. Right there, there's 4 million, so we're just a little bit above that. And then 6.7, okay, substantially above now. 6.7, we're almost up there at 6.75. And then the next one is off the graph that I gave you. So the compound interest starts out lower, goes through those points there, crosses over somewhere there, and continues off the graph in that way. There should be a little more scoop to that line, but not that much more scoop. So now, if you were going to recommend to Kamala which option she should choose, what recommendation would you make?
Oh, yeah, true.
Okay. Why is that an important question, everybody?
Well, simple one's higher. It depends on how many years it was the better option. She's going for short term, like only under 15 years time, then better off simple. She's going more than compound.
Cool. Yeah. So just like when you find like the point of intersection between two lines, that point of intersection is what we would call an inflection point, where it looks like they intersected about 14 years, and you could guess and check and find the point of intersection even closer if you wanted. But for our purposes, that's plenty close. If she's less time than that, it really looks like the simple interest is better. If she's more time than that, it looks like compound interest is better. And because these compound interest situations always increase their slope and their curving, they will always beat simple interest given enough time. Even 1% compound interest will beat 100% simple interest after about 600 years. It's a long time. Yeah. Now, I agree with you. You're right. I'll give you an even better answer. Use simple interest until you get to $2 million and then switch to the compound interest option so that you start earning 10% interest that's compounding when you have $2 million in the bank. Because 10% of 2 million is 200,000, and that's what you would have been making anyway if you just kept going with the simple, but then you start your compounding earlier. So that would be, if you had all the flexibility, you would be growing this way from there. So anyhow, that's comparing simple interest to compound interest. Now, another thing that we often do in our society is apply interest more often than once a year. If your investments are in the stock market, they can be going up and down every second. So when you have a regular period of time that's applying interest, we have a different vocabulary for those different periods. So let's take a look at the vocabulary here. The first one, if interest is compounded biannually, interest is applied twice per year, and then you have a C value of 2. So that would go into this formula. Future value is equal to the principal multiplied by 1 plus R divided by C raised to the power CT. So in this formula, take a look at what C is doing. If we're applying interest twice per year, what we do is divide the interest rate by 2 and then double the amount of times we're using that exponent. You're applying interest twice per year, so multiply the number of years by 2, and that's your new exponent. And your interest rate gets divided by 2, because you're only getting half of the interest rate every time the interest is applied. Okay, so that's how the C interacts with this formula and why you see it in two places. Okay, now if interest was compounded quarterly, how many times would that interest be applied each year? 4, once per season. So that's 4 times per year. And C would then be 4. If we were applying interest 12 times per year, what do you suppose the word for that is? Monthly. Good. Monthly. And C would be?
Biweekly.
12. This is biweekly. Good. And wouldn't you know, biweekly is 26 times per year, so C is 26. That's not so uncommon. A lot of people are paid biweekly, or we call that semi-monthly. Semi-monthly and biweekly are slightly different because there's not exactly 4 weeks every month. Compounded weekly means we're applying interest 56 times per year. And then the last situation would be compounded daily. That's actually not the last situation, but it's the last one we're going to look at. 365 times per year. And so then C would be 365. Oh, 52. Yeah, 52. Right. 52. Yeah. Made a mistake. I don't know why I did that. Don't know where I got the number 56. That's 52. After daily, continuously. Where every instant interest is going on to your investment. Hourly could be another one, yeah? Or they update it every minute. But if you compare that with updating it every instant, I don't think it would be a penny different on $1 billion. If you did it hourly or you did it every instant. It's very, very close, and it's approaching the same value. We're going to take a look at continuous compounding. It'll be the last thing I talk about today. Now, one thing that you'll notice is that in Delta Math, you often have to solve for how much do I need to invest today at a certain interest rate in order to have, say, $10,000 at a certain time in the future, at a given time. That can be useful if you want to, say, get a new car when you're 20, and right now you want to know about how much money do I need to put into a savings account to have $10,000 in 4 years. Well, you can answer these types of questions by rearranging these formulas. And once you have a good rearrangement of the formula, it gives you a new thing that you can plug and chug for different question types. So let's see if we can rearrange this formula for the principal. So what we like, our goal is to have a formula that's P equals and then some stuff here. So I'll give you a moment, see if you can rearrange this formula here, and then we'll carry on again. So let's take a look. Here's how we'd rearrange this to solve for P. I notice that I'm multiplying by this big annoying thing, and I would rather not be multiplying by that. Oh man, why do I lose my drawing tools? Happens sometimes. Okay, so what I'm going to do is divide both sides by 1 plus r over c raised to the power ct. 1 plus r over c raised to the power ct. There, we're done. Just one step. Because this divided by that is just 1, so it cancels. And so we have P equals future value divided by 1 plus r over c in brackets raised to the power ct. And that's the formula saying I need to invest this now if I know I want this much money at this interest rate with this compounding frequency for this long. Up here in this formula, we'll talk about it over here, this is what I'm multiplying my principal by. So that's the total factor of growth. That's what I multiply by to find out by how many factors it's grown. So if this was 10% and this was 1 year, this would be 1.1. So I'm multiplying my investment by 1.1. If I want to find how much do I need to invest today to have $1,000 in the future, I divide both sides by 1.1. I divide by this. I divide by how much factor of growth I could expect to have. So it makes intuitive sense in that way. And this is just a formula that you can just use. It's much more complex to reorganize and solve for the necessary interest rate to get a certain amount of money from one point to another point over a given amount of time. I'll show you the rearrangement. I did not prescribe these delta math problems. They're a little bit more challenging, but you can have this formula if you want it, and I'll show it to you right now. So here, to solve for r, in this case, I'm going to first divide both sides by p and get that out of the way, so that I have future value divided by p is equal to 1 plus r over c raised to the power ct. And then I'm going to take the ct root of both sides. And so that will be the ct root of fv over p is equal to 1 plus r over c. And I'm done with those brackets, so I don't need them anymore. So I can actually subtract 1 from both sides now to tidy that up. It's outside that radical. And then I'm going to have just r over c there. So that's going to be r over c is equal to what I have over here. The ct root of the future value divided by the principal minus 1. And then if I put this all in brackets and multiply both sides by c, those c's will cancel, and I have solved for r. So that's rearranging to solve for the necessary interest rate to achieve certain investment goals. Writing that out in a nicer way, r is equal to c multiplied by the ct root of future value divided by the principal minus 1. There. So that's that formula. Now the last thing that we want to take a look at is the case of continuous compounding. This is common in our society, so I find it strange that it's not required that you know this by the curriculum. It's also in the delta math. There's no way for me to take it out to spare you learning about this highly useful topic. So we're going to learn about this highly useful topic right now. We have a new formula that's even easier to work with when you have continuous compounding. But we all get to learn a new number, e. When did you first learn about pi? Tell me, was it grade 8? Was it grade 9? When did you learn about 3.141 blah, 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 blah? Yeah, grade 7?
Either
Yeah.
7 or 9.
And here we are, grade 11. Has anyone learned about the number e before? Yeah. The number e is a number like pi. It's a number with an infinite number of decimal places. The number of decimal places I've given you there, 2.718, should be enough for the detail that Delta Math wants you to have. If you find you need a little more detail, Desmos knows this number. You can just go into Desmos and punch the letter E, and it will tell you that E is 2.718. Was it 28? Yeah, so 1828182846, etc., etc., etc. Off to infinity. It's a special exponential number that has to do with exponential growth in a similar way that pi has to do with circles. So we're going to be using that for the continuous compounding. That's where interest is applied every instant based on your interest rate. So they take, let's say it's 12% interest over the year, divide that by infinity, and apply that infinity times. And it works out to be your principal multiplied by this number e raised to the power rt, where r is the interest rate as a decimal and t is time in years. And that will be what your investment is worth in the future. So to check your understanding, try these problems, and I am going to go ahead and start doing some Delta Math walkthrough for you to show you how to answer these questions. That way you'll see me apply C and how that works in different problems, and I'll be able to show you some examples. Okay? And any questions for Team Learn at Home, hit me up by email. Thanks very much, everyone, for showing up for your learning.